In this video, we are going to define the notion of a Cauchy sequence of real numbers. So we will work through this definition in just a moment. Then we will have a couple computational examples and look at some results, some theorems about Cauchy sequences. I put up here also completeness of the set of real numbers. I've decided to make that the next video. So I might touch a little bit on this idea of what it means to say that the set of real numbers is complete. This is a word that we've thrown around a couple times, particularly when talking about the supremum property, if you've been following this course. In the next video, we are going to do a full study of what it means to say that the set of real numbers is complete. All right, let's take a look at this definition. I think it's a good idea at this point in the course for you to pause and work through this clause by clause. The flow of this definition should sound familiar to you because it's stated like a real analysis theorem. We have for any epsilon greater than 0, there's a capital N. That should remind you of the definition of a convergent sequence of real numbers. And in fact, if you have notes on that handy, I think it would be a good idea for you to pause, read through this, read through the definition of a convergent sequence, and see what they have in common, what's different. Is there any connection between the two definitions before we work through this together? Let's read through this definition together. We say that a sequence, A sub n, is Cauchy. That's a person's name, Augustin Louis Cauchy, French mathematician. A sequence is Cauchy if for any choice of positive epsilon that you make and fix, so fix this value epsilon. With that, you can then go find some threshold index, capital N, so that if you take any pair of terms beyond that threshold and look at the distance, so here think of this as a distance, the distance between their corresponding sequence terms, that distance is less than epsilon. So let me sketch a picture of this. I can't draw infinitely many terms, but what I can do is imagine that the beginning of my sequence I don't think you can see that. Let me take a different marker. Blue is kind of hard to see. Okay. Let's try again. The beginning of the sequence can do whatever it wants to. Okay, so maybe that goes on for a while. And then here's my threshold index capital N. Say this is the term A sub capital N. If I take any two members of the sequence beyond this index, it's an infinite tail. There are infinitely many such terms. If I take any two, like maybe this one, maybe that's n plus 2, and then this one could be a billion terms away, the gap between them vertically, so their distance to each other, which, okay, let's see, it's about like this. That's supposed to be a distance. This is less than epsilon. Okay, that looks like I less than epsilon, sorry. But the point is that these two terms are close together. And we can do that for any pair of terms beyond this threshold. So in particular, if capital N is 50, well, we could actually even pick it. That's fair with this inequality. I could pick the 50th term and compare it to the 100th term, or the 100 millionth term, or the trillionth term in the sequence. There are a lot of pairs of terms that you could pick beyond this threshold, and they can be very far apart. But any pair of terms that you pick beyond this fixed threshold will satisfy that the gap, which here you think of as this vertical distance between their corresponding sequence values, is less than epsilon. All right, let's just make a couple of remarks here about the way that this definition is phrased. I don't think that this will surprise you at this moment, but when you say, for any choice of epsilon greater than 0, after reading this, from this moment forward, for the rest of the definition, you think of this value here as fixed. All right, so it's like fix some choice of epsilon. It's a positive number, but mentally you want to imagine that it's very, very small. That's where the power of the statement comes into play. So I like to imagine that epsilon is 1 billionth, just to give it like a sense of scale. It's a very small number. With that choice of epsilon, I can then go find a capital N. So while I typically write capital N, sometimes you'll see notation like capital N sub epsilon, or even N as a function of epsilon, to emphasize that this choice you're making here, this kind of anchor for the rest of the statement, is based on how you picked epsilon. So it's almost always, like, very, very rarely is it not a function of epsilon. Basically, if it's a constant sequence, it doesn't matter, but it's a function of epsilon in general. Okay, so given this epsilon, we pick a threshold, and then we have this chain of inequalities here. I order them because I think it's convenient when we work out computations with Cauchy sequences to situate m as greater than or equal to little n. Sometimes a different text may say just any pair of indices m and n without ordering them, but it's just two numbers, so you can order them relative to each other, and I choose to do that. I think it's cleaner than just stating it's a pair. Okay, so any pair of indices beyond this threshold will satisfy this distance measurement. Before we move on, I want to compare this to convergent sequences. At this point, you should be able to rattle off the definition of a convergent sequence. So if somebody stops you in the street and says, quick, what's the definition of a convergent sequence? I hope you would be able to say that a sequence of real numbers a sub n is a convergent sequence with limit L if, given any choice of epsilon greater than 0, there's a threshold capital N from the set of natural numbers, so that if you pick any index beyond the threshold, the distance between the corresponding sequence terms and that number L is less than epsilon. So some variant of what I just said, which communicates the same idea. This is phrased almost exactly the same way, but we do not have a limit in this statement. So nothing about this definition, the way that it's stated, insists that the sequence has a limit, and it may not. That might surprise you, but we will actually talk about that more in the next video when we come back to this idea of completeness. So I'll just say it there, that this is not exactly the same definition as convergent. As a first example, let's prove that the sequence 1 over n, so 1, a half, a third, a fourth, etc., is a Cauchy sequence. This is going to be a direct proof, so it's going to follow the flow of the definition. Now, often when you write proofs of convergence or Cauchiness, as we are doing in this video, you might have scrap work, or you might go through several drafts before you have a professionally composed proof. I'm going to jump right into this. Maybe we'll do some scrap work in the next example. As is often the case when you have a definition like this, where you are starting with this notion of fixing an epsilon, that's going to be how we open the proof. So often I will write, let epsilon be greater than 0. From this moment on, for me, this epsilon is fixed. Some people really like to insist on the phrase be given, which I will do for this example. Okay, I know that's the first thing that has to come because that's how our definition starts. So we fix an epsilon greater than 0, and then we go find some threshold that will work for it. I don't actually know what that threshold is going to be yet because we haven't done any scrap work, but here's how we can keep going with this nicely composed proof. I'm just going to leave myself space to fill it in. So given this choice of epsilon, choose n from the set of natural numbers so that, or such that, n is greater than something. So just leave myself some space here. And I trust that in my distance measurement computation, what this threshold has to satisfy will become apparent to me. Okay, we'll do scrap work in the next example, don't worry. Whenever little m is greater than or equal to little n is greater than or equal to this threshold capital N, we find, okay, comparing this to the definition, we have fixed a choice of epsilon. We have then found a threshold index, which we will choose actually at the end so that it works for this computation. So it's like, we're going to work out what this blank has to be. Then if I take any two indices beyond this threshold and look at their corresponding sequence terms, we need to say that the distance between those terms is less than epsilon. So what is the distance between those terms? Let me see if I can squeeze it all here. So that's the distance we need to compute now. Well, we have explicitly what these terms have to be. That's 1 over little m minus 1 over little n inside the absolute values. Okay, common denominator. I like working down the right-hand side. I might have to start working to the right, though, if I run out of room, but let me see what we can do. With a common denominator, that's going to be n minus m over mn, like that. Because I have ordered m and little n relative to each other, I know that the absolute value of n minus m, or rather, let me start by saying the quantity n minus m is negative. To take the absolute value, I need to flip it. So we can remove the absolute value if I rewrite this numerator as m minus n. If you don't see that, check with numbers. And then m and n are both positive natural numbers. So we just drop the absolute value at this point. Now I'm going to start writing to the right. So on paper, if I were writing this on notebook paper, I would keep going down because this is nice formatting for this kind of computation. But, this is the dream, is to keep going down the right-hand side. However, I'm going to run out of room. So let me move to the right now. I'm going to start thinking about how to adjust this so that if anything, we only go up in size. Now, if you make the numerator larger, you make the fraction larger. So we actually go up in size if I just replace this numerator with m and don't subtract off n from it, because that's going to give me a smaller number. So go up in size by rewriting the numerator as little m only. So m is a bigger number than m minus n. And now this is lovely actually because the m's cancel, leaving us with 1 over little n. Make the denominator smaller makes the fraction bigger. So if I replace little n with the threshold, if anything, we go up in size. And I would like to now say that this is less than epsilon. That is true if I knew that n was greater than 1 over epsilon. Okay, let me finish this here. I think I can squeeze this here. Thus, A sub n is Cauchy. It's a direct proof, so you don't need a long conclusion. Okay, sorry about running out of space. Let me make a couple remarks about this example. If you are watching this and you did not look at how we proved convergent sequences, you might have gotten lost here. I kind of talked through the mechanics of doing this sort of knockout process when we studied convergent sequences. It's a very similar idea here. We have a distance measurement that we want to bound above by epsilon. So as we simplify, we can always go up in size if we can then show that this larger term is less than epsilon. Because if this is less than epsilon by transitivity, so is this. So as you work through these kinds of maneuvers, where you're always going to start this kind of computation this way by comparing these terms to each other. Often you'll have an explicit form for your sequence. Here I have equality, equality, equality. At this point, I've got a lot going on in this fraction, and it would be cleaner if I could just throw away the minus n from the numerator. And you can do that if you go up in size. So anytime you're working through this kind of computation, go up in size so long as you can get to epsilon as the cap at the end. Because again, if this is less than epsilon and this is smaller than this intermediary step, then this is less than epsilon. So just keep in mind, go up in size, that's okay. All right, so the computation checked out. If I had done the scrap work, which I will do in the next exercise, I hope I didn't jump into this full write-up too quickly. In the next exercise, we'll kind of work out this computation maybe less formally first. But if I had done the scrap work, I would have seen exactly this. So I would have just started here, kind of worked through this and gotten to this inequality so that when we wrote the proof, we would immediately know what had to be true about the threshold index capital N. However, once you have written enough of these proofs in your life, and I think I'm at that point, you can often start with this kind of preamble because you know how it's going to go. So it's like, I know the proof is going to start this way, so let me just go ahead and write it down. And then leave yourself space to make that final judgment call. I trust that I'm going to get to some relationship between capital N and epsilon, but I don't necessarily know what it is the moment I start the proof. But I can work it out and then go back and fill it in. So that's what I did in this particular case. Okay, let's look at another example. Our second example is the sequence of terms of the form a sub n equals 4 plus 2n plus 3 over n minus 1. So this sequence is not particularly meaningful or exciting. The goal of this example is just to practice doing correct algebra. I just want to show you an example that's a little bit more involved than the sequence 1 over n that we just worked with. So let's open by doing scrap work. Typically with this kind of computation, you often want to experiment with the quantity inside the absolute value before you jump into the proof. All right, so this is that distance that we're interested in. This is just scrap work. So we know that our goal in the proof will be to fix an epsilon greater than 0 and have a threshold. Let's see what would happen when we come to this evaluation step. Here, this is an m. Okay, it's going to look like 4 plus 2m plus 3 over m minus 1 minus 4 plus 2n plus 3 over n minus 1. Right, so the 4's cancel. So one of the messages I want to communicate with this example is do not start knocking things out at this stage. I see students sometimes when they're still within the absolute values trying to get rid of terms they don't like because there's a lot of multiplication that has to happen here in order to simplify this expression. I would advise you not to do any of those knockouts, adjusting numerators and denominators, until you have simplified what's inside the absolute value and done the absolute value. Because when you have subtraction and you don't even know the sign of this yet, there's a chance that you're actually going to make your quantity move in the wrong direction. So it's always dangerous with subtraction inside of absolute values to start adjusting terms unless you really know what those terms are doing. So I've seen it happen that students start trying to knock stuff out and they've made a mistake, which means that to proceed with this, I'm just going to combine these fractions into one with a common denominator. All right, so we have to do some multiplication, but that's okay. A lot will cancel. And honestly, sometimes if you just admit that you have to do this, you'll end up saving time than if you try to fight it. So let's just go ahead and do this. All right, multiply everything out. We have 2mn minus 2m plus 3n. Just watch your m's and n's. Again, the point of this exercise is really more algebra. And then let me leave it as this product. Okay. As promised, we have two very similar expressions here. You should expect some cancellations. So this cancels with that, getting rid of the mn terms. The constants cancel. We are going to have a total of negative 2m minus 3m, so that's negative 5m, 3n minus negative, so 5n. Okay. Again, if you just do it, it's going to be faster than if you start trying to figure out what you can legally do. Okay, now that we've simplified this as much as possible, I think we're ready to take the absolute value safely and know that the end result is going to be a positive number. The 5 I can pull out front of everything. We actually have an expression in the numerator similar to the previous example. It's n minus m. In my typical way of talking about Cauchy sequences, little m is going to be the bigger index. So n minus m is negative. I need to flip it and write m minus n. And then the denominator is already positive. Okay, this doesn't look too hard, but if you start expanding this denominator and trying to kick out terms, actually it's more challenging than you might expect at first glance. So if you just start trying to knock out the n, the problem is that here, the most natural thing to do would be to perhaps make, I think I'm going to do this two ways. Okay, let me do way number one. I am going to make the denominator smaller to make the fraction larger. Let's leave that as n minus n for a moment. This is the product of two numbers, two positive numbers. If I shrink one of them, the product gets smaller, the fraction goes up in size. So in particular, let me take m minus 1 and decrease this factor by replacing it with m minus n. Right? So if m is 50 and n is 10, m minus 1 is 49, but m minus n is 40. And this product would be smaller than that one. And now this is wonderful. because these cancel, leaving us with 5 over n minus 1. If I kick out the -1, I make the denominator bigger. That makes the fraction smaller. Don't do that. At this point, just leave it. So, the next step to do would be to replace this little n with the threshold and set that less than epsilon. Okay, so at this point, we have a nice expression, which when we set less than epsilon, will give us something pretty clean to work with. Now, this is what I wanted to do. And then as I started to speak, I had a moment where I thought, oh no, I see a nice simplification too that people might like better. Let me pause for a moment just to make sure that my algebra is going to check out. It did not work. I'll show you what I tried in just a moment. I think this is still the nicest approach to this simplification. You might see a different maneuver that you can do. So it's not that there's only one way to proceed. What I was thinking a second ago, and I was like, I just don't know if this is going to work because it's actually messy when you start trying to knock out terms, is let's make the denominator smaller by taking this factor and replacing it with n minus 1. M is bigger than n, so we go down in size. If I write the denominator as n minus 1 squared, okay, so replacing that with n, smaller number. But then my next thought was to go up in size by replacing n with 1. Like I just saw the ones there, but I have an m and an n, and that's not good. So, oh wait, that's fine. Actually, let's fix this. Okay, this is not great the way it is, but why don't we just do that numerator replacement only? Yeah, this is fine. Okay, new idea. Don't change the denominator, change the numerator the way I just said. We go up in size if m minus n is replaced with m minus 1, because little n is greater than or equal to 1. In fact, for the sequence, it has to be greater than or equal to 2. And now we can cancel, and we get, well, I've left off the 5. 5 over n minus 1, and you see we actually get to the same place. Okay, and that should be minus 1. All right, so the take-home story here, like the reason why I wanted to do this example, is really just to emphasize that you should not try to adjust your terms too early. I have seen students make mistakes where they tried to knock out a term and maybe just for that one fraction it's okay, but it's inside of a subtraction expression. If you make a negative number bigger, when you take the absolute value, you've made it smaller, right? So don't try to make adjustments too soon. Simplify as much as you can with equality, until you get to a nice expression. Here, I can take the absolute value cleanly, and then I had 2 ways to proceed. If you try to expand this and start knocking out terms, I think it can actually be harder than you think at first glance. At least it was for me. So when I saw this replacement, I thought that was nice. Likewise, m minus n, replacing that with m minus 1 to get the cancellation was nice. And I think we are ready to go. Let me quickly write out, I'll probably leave it on the board here, that we're going to have 5 over epsilon, less than capital N minus 1. So 1 plus 5 over epsilon will be our lower bound for the threshold capital N. So we've solved for a threshold that will work for our given choice of epsilon. When I write up the proof in just a moment, because this computation is so huge, I'm going to go from here to here. So I'm going to not write this all again just because you're going to watch me write out the same thing I already wrote down. But if I were writing this up nicely and giving it to someone to read, I probably would include most of this. A lot of it is just routine algebra. It doesn't really feel like real analysis, doing expansion and canceling of terms. But don't leave too much work to the reader. Do help your reader follow your steps. If it's equality, jumping from here to here, it's okay. But help your reader along. I would never skip steps where I knock terms off. So I would never start here and then suddenly say that's less than or equal to 5 over n minus 1. That's not fair for the reader at all. So when you start making these kinds of adjustments, do include those steps so that the reader sees where the bound, like the new terms are coming from and why it works. Don't leave too much for them to do, because I read a lot of these proofs and sometimes I have to really work through to try to understand what a student is proposing as an adjustment for their terms. Okay, so this proof will go quickly because I'll write down this, and we will wrap up this exercise. The formal proof is going to sound just like example 1. So I will say proof, let epsilon be greater than 0. And I'm just going to say that if I write let epsilon be greater than 0, period, at that moment I have fixed epsilon. It is not specified. It's a fixed positive number. Again, some people will insist on the phrase be given. I do not insist. Let epsilon be greater than 0. Choose some natural number, capital N, so capital N from the set of natural numbers, such that N is greater than 1 plus 5 over epsilon. One thing you can always test with this kind of statement, both for Cauchy sequences and convergent sequences, is if epsilon gets smaller and smaller. We consider 1 millionth, 1 billionth, 1 trillionth. You should expect your threshold to get larger and larger. So it's like the smaller you want to squash your sequence terms together, the farther out in the infinite tail of the sequence you're going to have to go to see the desired behavior, and that's what we see here. I just mentioned that because this is a little bit larger of an expression than we've had in the past. Then whenever little m is greater than or equal to little n is greater than or equal to this threshold, we find, just following the flow of the definition, a sub m minus a sub n is equal to the work that we did in the scrap paper, which we know will eventually simplify quite a bit. And let's see, I've erased it, but I believe it was negative 5m plus 5n over m minus 1 times n minus 1. So I wanted to pick up there. All right, that is going to be equal to 5 times m minus n minus 1, n minus 1. Wanted to mention one more thing here. And again, I'm focusing really more on the mechanics of writing proofs at this moment. I recommend computing the absolute value when possible with equality. So again, going back to don't start making adjustments too soon. At this moment, there's something that we need to do. We need to take an absolute value. So go ahead and take the absolute value. It can be confusing when you go from this to having knocked off terms. Okay, so again, keep equality until you get to a nice expression that you've taken the absolute value of, it's positive, and then start making adjustments. And in particular, I'm going to say that this is less than or equal to 5 times replacing the numerator with a larger expression. So m minus 1 is greater than or equal to m minus n. And now we can cancel those. So this is equal to 5 over n minus 1. Continuing over here, we will go down in size if I replace little n with the threshold. A smaller denominator, a larger fraction. So this is the right direction to go. So we have 5 over little n minus 1 is less than or equal to 5 over capital N minus 1. And then it's like, do I want to just jump straight to epsilon? That's going to be less than or equal to 5 over n minus 1 is greater than 5 over epsilon. So if I replace n minus 1 with 5 over epsilon, my denominator is smaller, the fraction is bigger, 5 over epsilon. The 5's cancel, 1 over epsilon is equal to epsilon, so I will go to that. Thus, an is Cauchy. Okay, that concludes our second computational example. I'd like to talk more about properties of Cauchy sequences now. So I would like for us to prove this result now. Every Cauchy sequence is bounded. This is the kind of statement in mathematics where if you can sketch it and can create an illustration of a Cauchy sequence, you will see what the proof will need to do. So kind of like I did in the opening, let's imagine that we are graphing a Cauchy sequence. The x-axis is for the indices in the sequence, because the sequence is a function whose domain is the set of natural numbers. So if I graph a sub 1, it might be here. A sub 2 might be here. A sub 3 might be here. 4, the beginning of a sequence can be unpredictable. But for some choice of epsilon, there is a threshold in the sequence. Let's say that value is here. So that any pair of terms beyond this threshold, when compared to each other, have a vertical gap in this graph, which is less than the choice of epsilon that we made before we picked this threshold. Now, in this statement of the theorem, we are not trying to prove that a sequence is Cauchy. We are told that the sequence we're considering is Cauchy. We're trying to prove that if a sequence is Cauchy, then it is bounded. So I don't need to actually work with an unspecified epsilon. I'm allowed to pick one. Let's have epsilon just be the number 1. That's a positive number. Every pair of terms beyond this threshold, when compared to each other, should be within distance 1 of each other. Maybe I should rephrase this a little bit. I picked this, and then I picked the threshold. That's really the correct logical ordering. Okay. But for the sketch, what I'm going to do is imagine going down by 1 unit from the value of a sub n and going up by 1 unit. So this is like a sub n plus 1, and this is a sub n minus 1. A sub n is allowed to be one of the members of the pair that we pick, right? So capital N is part of that chain of inequalities. We have little m is greater than or equal to little n is greater than or equal to the threshold. So I can go ahead and pick this one, and then any term beyond. Here, here. All of these terms need to be within distance 1 of a sub n. What I'm trying to say is every term in the sequence beyond the threshold is going to live between these two horizontal bands. Or in other words, in this horizontal band. So what we have here is a threshold beyond which we can bound the behavior of the sequence terms. Now, in the beginning, our terms might jump around. One might be really high, really low, but that's okay because it's a finite collection of terms. So you can always handle the first finite number of terms in a sequence manually. Now, looking at this, it's like, okay, let's pick a bound that works for everybody. So we will have our bound capital B be the maximum of the size of the first term, the size of the second term, all the way through the size of the final term that we encounter before the threshold. And then after that, everybody is between these two numbers. The way I've sketched the picture, capital A sub n plus 1 would be the correct upper bound, but if this were negative, it would be the bottom side. If you do, well, you could do both. Okay, so if a sub n is positive, this is the right bounding quantity. If a sub n is negative, this is the right bounding quantity because we'd be down here. Whoops, sorry. By the triangle inequality, you could cover both of these cases if you wanted to with the quantity absolute value of a sub n plus 1. Okay. So this is the spirit of the proof. I will write it up in just a moment, but we are going to say this single bound, if you want, or pair of bounds, works for from the nth term in the sequence to the rest of the term. So the infinite tail of the sequence, this handles the beginning of the sequence. Overall, this number b, which is the maximal element in a finite set of positive numbers, or rather non-negative numbers, this will be bound for the entire sequence. Okay, so I did that kind of quickly because I'm going to write up the formal proof in just a moment. But again, it's important that you understand why the illustration leads you to the correct form for this bound b. If you understand what a Cauchy sequence is, you realize that the infinite tail of the sequence can be squeezed between two measurements based off of even just a threshold term. So saying any pair of terms at or beyond this threshold is, here I'm saying like a sub n minus a sub n is less than 1 for all n greater than or equal to n. This is really the statement that I'm using here. So any term beyond the threshold is within distance 1 of that threshold term. And because this is anchored down, capital N is something that we will identify in the proof. We anchor this number, add and subtract 1 to it, and that gives us a bound for almost everything in the sequence. And then the first few terms, we just manually include those in the bound computation. Okay, I think at this point you've got it. So let's write up the formal proof, and then we will have one more statement to look at. Here's how I would formally write up the proof of the statement that we just worked out an argument for based on a sketch. There's no named sequence in this statement, so let's go ahead and name it A sub n. So let A sub n be Cauchy. We know it's a Cauchy sequence. Thus, given epsilon not equal to 1, this subscript 0 is just a choice I make when I write these kinds of proofs where I'm emphasizing that we are allowed to fix an epsilon because the Cauchiness of the sequence is already known. So for me, this is like whenever I make a specific choice of epsilon. Thus, given this choice of epsilon, namely the number 1, there exists a threshold index from the set of natural numbers such that for all, I think I will stick with the definition of Cauchiness just for now, m greater than or equal to n greater than or equal to the threshold, we have a sub m minus a sub n is less than epsilon naught. My hesitation was that I'm not going to use two arbitrary terms in this way, but by writing this out this way, I'm kind of reminding the reader of what the definition of a Cauchy sequence is. Okay, now let's really get specific to create this bound. In particular, for any little n greater than or equal to the threshold capital N, we have, so how about observe that the distance from a sub n to this threshold term, which is fixed because n is fixed, is less than 1. Okay, so my first sentence kind of reminds the reader what it means to have a Cauchy sequence. And then with this phrase in particular, I'm zooming in on something specific that we're going to create for this Cauchy sequence. So namely, I'm just going to compare terms beyond the threshold to the threshold term itself. And I'm also bringing in the specific value of epsilon that we chose for this Cauchy sequence. I.e., in other words, let's unfold this inequality. So -1 is less than what's inside the absolute values. I'm like really running through these markers today. There we go. Is less than +1. Add the fixed term, right? So this is an anchored term. We know what capital N is. It has a precise value. This is unspecified, so we have to be careful here. Add a sub capital N through to everything. A sub capital N minus 1 is less than a sub n is less than capital N plus 1. All right, so now when you take absolute values, it's like if these are both positive, then this absolute value is less than this one. This is negative, then this one is negative, so this absolute value is bigger than this one. All that to say that thus the absolute value of a sub little n is less than the maximum of the absolute value of the left side and the right side. And then if you apply the triangle inequality to both of these expressions, you'll get the same expression. The absolute value of a sub capital N plus 1. And that's nice because it just gives us one bound where we don't have to worry about, the size. All right. And that handles almost every single term in the sequence. So for all n greater than or equal to the threshold, they're bounded by this fixed quantity, where again, this is fixed because capital N is fixed. This is a number that I have picked and anchored down based on making this choice of 1. Let B be the maximum of the size of the first term, because that could be something really unpredictable, the size of the second term, all the way through, however many terms we have before that threshold, like that, and then this expression. This maximum does exist because this is a finite set of non-negative numbers. It has a set maximum. And at this point, it's so cleanly constructed, you don't really need to prove to the reader that this is a maximum for everything. If we look at the first term, it's equal to this. So it's less than or equal to b. Second term is equal to this. Literally, it's spelled out for us. So it's less than or equal to b all the way through the next to last term, before the threshold. So the n minus 1th term. And then at the threshold and beyond, we did prove that this bound works. So this is when I just say the phrase by construction, meaning as the reader, you should be able to understand why this construction is the correct one. By construction, a sub n is less than or equal to b for all n, taking us all the way through every term in our sequence. Thus, it's a bounded sequence. All right. It's a nice proof. It's a familiar proof. If you had a feeling of deja vu, either when we were doing the sketch or when we worked through this write-up, it might be because this proof sounds almost exactly like the proof that convergent sequences are bounded. The only difference is right here. If you revisit the proof that any convergent sequence is a bounded sequence, we have exactly the same construction, except this threshold piece is replaced with the limit L. So in our picture, instead of comparing terms in an infinite tail to like one fixed term in the sequence, we compare them to the limit value, but otherwise it was the same construction. So again, you start to feel like there's some connection between Cauchy sequences and convergent sequences that I have not yet made precise. I'm not going to make it precise in this video. I will in the next video, but I do have one more result for us to look at. Let's wrap up this video with this exercise. This is not really a deep theorem in mathematics because we're going to have in the next video a much stronger connection between being a Cauchy sequence and being a convergent sequence. So this is really like an exercise for you, especially in proofwriting, brainstorming and proofwriting. So what we have here is a sequence that we know to be Cauchy, and we've identified a subsequence which converges to some real number L. With that information, we want to show that the entire sequence is convergent and converges to L. So I really want you to try to work through this on your own. What I would like for you to do is, in a moment, pause and do as much as you can. So you can sketch a picture, you can start kind of working out what needs to be shown. Maybe you'll get the whole thing. I will come back in a moment and give you a hint and then maybe another hint, however many, until we have the full argument laid out. All right, so here's my first nudge if you haven't gotten very far. You are being asked to show that a sequence converges. At the end of the day, it's a proof of sequential convergence. So what needs to be shown in order to verify, usually directly, that a sequence is convergent? So what kind of expression do you work with? When you want to write a proof, often a direct proof that a sequence converges, on your scrap paper, what you might write is this. We would like to conclude that this measurement is less than some epsilon that we will formally introduce in the proof. So this is just scrap. If this were an explicit sequence, you might have an expression here and a number here, but this is the same idea. I want to compare sequence term a sub n to this limit L without really having a value there. So my next hint is I cannot compare these two quantities directly to each other. I don't know enough about a sub n on its own to conclude that it gets really close to L. Is there anything that I could compare each of these two individually, separately? Like basically, do they have a mutual friend? Is there something I could rather compare a sub n to and something I would rather compare L to? Just rereading the statement, you might realize like, well, we haven't brought in this expression yet, so that might be the answer. A little bit more deeply, you might realize that a sub n is a Cauchy sequence. So I would like to compare it to another term in the sequence. Like if I could bring in another, what you might think of as a sub m, although we're going to write it with this specific form in just a moment. So for a Cauchy sequence, we want to compare terms to each other, but we also have that this is a convergent sequence. So I would like to compare the limit to the sequence I know converges to it. So both of those themes are leading me to bring in a way which doesn't change the expression because it's going to cancel itself out. I want to bring in some kind of subsequence term. Now this again is just scrap work, so I'm not really saying where these are. There's no epsilon yet. We're just brainstorming. All right, this is good because this comparison reminds us of having a Cauchy sequence. Maybe these two terms are far out in the sequence beyond some threshold. And then this is good because the subsequence converges to L. What do we do when we have this kind of pair of pairs inside an absolute value? This is one of the reasons why we use the triangle inequality so much in mathematics and real analysis, is that we often bring in a mutual friend like this. It's like to get from here to here, we go through an intermediary, and then we can break that up using the triangle inequality. We will set up our presentation of A sub n as a Cauchy sequence in such a way where when I compare terms, a pair of terms in the infinite tail that we'll define precisely in just a moment, the comparison between them will result in a measurement less than epsilon over 2, and that is legal, right? So you're saying like for any arbitrarily small number, you can then go find a threshold so that any pair beyond that threshold will be smaller than your choice of upper bound, and here it's going to be epsilon over 2. Okay. And then similarly, when I mention that this subsequence, A sub n sub k, converges to L, again, we'll pick a threshold for that subsequence so that the comparison of terms beyond the threshold for this sequence and the limit results in a distance measurement which is also less than epsilon over 2. So let's see, we need a couple of thresholds here. I want to mention this before we erase the scrap work and do the formal write-up. The first thing we need is a threshold, which I'll call n sub capital 1, so that here, this is just a statement about being Cauchy. What am I writing? Little m greater than or equal to little n. That looks like an m, but you probably know what it is at this point. Beyond this first threshold implies a sub m and a sub n are within distance epsilon over 2 of each other. Okay, here I don't want to bring in the subsequence yet because I'm not sure how to pick this index. So I just want to say pick a threshold for the entire Cauchy sequence so that all pairs beyond that threshold are within distance epsilon over 2 of each other. Now, this is a sequence in its own right, so its subscripts go off to infinity, which means eventually they will land beyond n sub 1. So here we want to choose, let's just call it, I'm trying to think, k. How about k? Maybe I just need n then. I'm going to make a little modification. This is scrap work. We'll have a subscript lower bound here, k, such that for all little k greater than or equal to k, n sub little k is greater than or equal to n. That should work. And that's not really all that I need. I also need it to be big enough to drive the subsequence close to L. Okay, so actually let's have this be K1. All right, so we got to pick one threshold for the subsequence so that if I take any subscript down here, larger than that first threshold, K sub 1, we know that we're going to land in this world. But also we need this behavior to happen. So it's like we need to arrive here and have this. So the subsequence index has to do two things. K2, such that for all k greater than or equal to K2, this. And then we'll pick the maximum of these two. Maximum of the two. All right, so since we have the subsequence here and here, we need to make sure that our terms land in this regime, but we also need to make sure that we're getting this bound. So that's why I have two thresholds here, and then we'll just say, hey, pick the maximum of them, and that way, for all subsequence terms whose real index here is k, n is fixed, k is the index. For all k's beyond this k, this is true. Okay, so let's write up this proof now. I think we have everything we need. This is our last proof in the video, so let's write a really nice one. Let epsilon be greater than 0 be given. Since an is Cauchy, choose an appropriate threshold. So choose capital N from the set of natural numbers such that for all pairs of indices at and beyond this threshold, it follows that the distance between their sequential values corresponding to these indices is less than epsilon over 2. Okay, so for all pairs beyond this threshold, when we look at the corresponding sequence terms and measure the distance between them, that is less than epsilon over 2. You're allowed to do that. We know it's a Cauchy sequence. So whatever right-hand side I want to have here, I can go find a threshold that squeezes this below that number. And in this case, that number is epsilon over 2. Okay, let's see. I think I can now just go ahead and choose that first capital K index. So choose K1, capital K1, from the set of natural numbers, such that for all little k at or beyond capital K sub 1, in k is greater than or equal to, n sub k rather, is greater than or equal to this threshold n. Okay, that just puts our sequence terms into this comparison, basically. But now we also need to drive them close to L. Since A sub n sub k, the subsequence converges to L, choose K sub 2, capital K sub 2, such that for all little k greater than or equal to K sub 2, the distance between the corresponding term and the subsequence, which the corresponding term is indexed by that k. Okay, so A sub n is like fixed notation, and we index through the subsequence with this second subscript k. If this feels a little exotic, you might want to revisit our video on subsequences. Okay, A sub n sub k minus L is less than epsilon over 2. All right. And again, you can do that. We know we have a convergent sequence. So if I want my sequence terms here, my subsequence terms, to be within distance epsilon over 2 of L, this is just a positive measurement over here. I go find a threshold for this measurement. So the threshold that you pick is really depending on what you want on this right-hand side here. All right, we have two thresholds now controlling the behavior of the subsequence. We would like for both of the behaviors to be simultaneously true to ensure that we pick the maximum of the two. Let K be the max of K1 and K2. I'm going to do something here which I didn't make clear in the scrap work, but I will talk through it at the end. I am going to pick one specific subsequence term. So now it could even be n sub k. Yeah, let's just actually go with that. I'll explain what I'm saying in a moment. All right. Observe. I think I'm going to write this to the right here. For all n greater than or equal to capital N, A sub little n minus L. This is the comparison that we want to make to show convergence of the entire sequence A sub n to L. So there's no mention of the subsequence here. We are trying to prove just plain old convergence. To do that, as we talked through a moment ago, we are going to bring in, I'm trying to emphasize that this is capital K here, this one specific subsequence term. So this is actually n sub capital K. We bring it in without changing the value of anything. talk through that again in a second, but let me keep going to finish out the argument as we saw in the scrap work. I will run out of room, so let me go ahead and apply the triangle inequality right now. So you can break up that pairing, or break this into two pairs. Because little n is greater than or equal to capital N, and so is n sub k by construction. So this is a specific number down here. It's greater than or equal to k1, which means that n sub k is also bigger than n. So this pairing is less than epsilon over 2 by this statement. Okay. But similarly, this fixed index down here, n sub capital K, is greater than or equal to k sub 2, which means that its distance to L is also a value less than epsilon over 2. Hence, A sub n converges to L, and we are done with the proof, but I want to say something about it. The thing is, this is not a statement about the subsequence. The statement that we were asked to prove was just about the sequence. So if you look here and here, it's just proving a sequence converges to L. When you do that, the index n right here, this must be general. We're trying to say that given this choice of epsilon, there's a threshold out there so that for all terms with an index at or beyond that threshold, the distance from the corresponding sequence term to this limit L is less than epsilon. Now, if you bring things in, these do not need to be done in generality. I've already anchored down at this point capital N and epsilon. So all of the selection here of k's is based on fixed numbers. So you don't need to say, and for all little k beyond capital K. That's more general than you need. I'm just bringing in one value here, which will allow me to split this up and use the Cauchiness and the convergence that we are already aware of. So there was no need here to have a general subsequence term. I actually just picked, like, if I graphed out the sequence, I just picked one specific dot and said all terms beyond the threshold are going to be compared to this one dot. And the name of that dot was A sub n sub capital K. So you can write it in generality. You could say, for all n greater than or equal to n and k greater than or equal to capital K. It just feels for the reader a little bit strange because this is not a statement about k right here. It's just a statement about little n. So little n had to be general to establish convergence. Capital K here actually didn't have to be a general index beyond some threshold. It could be specific, and that's what I made it. Okay, you might need to think about that for a minute. I am done with this lesson. I wanted you to work through this proof step by step when I presented it at the beginning. And in particular, I wanted you to get to this part and kind of recognize how each of these was going to use the hypotheses that we had to get to epsilon. But then I kind of took over with that selection of the thresholds. I meant to let you have a moment to think about what kind of thresholds need to be picked. So since you've now seen this, what I recommend doing, and this is honestly often my recommendation, so not just for this proof, but many of the proofs that we do, give yourself 30 minutes, tomorrow, something like that, and try to prove this statement again without looking at your notes. So this is always something to do when you're learning to write proofs, is you might understand in the moment, or you might feel like, yeah, okay, I see how this proof is what it is and why she made all those remarks. But to really check if it sticks and if you're writing proofs correctly, you really do need to give yourself a little space and then try them again. So while I had you brainstorm on your own some in this proof, do readdress this later. I think it's a good exercise. All right, let's wrap it up. Thank you for your attention.